Hello, so we're going to do a quick walkthrough of the bond energy lab. So in our unit, we had an opportunity to do a lab where there wasn't a procedure written out. This is the template. This is what you'll be turning in online. And you may not have had the chance to do the experiment, so I'm going to show it to you here real quick. One of the main ideas is that we're taking a solid ammonium nitrate and we're going to dissolve that in water so that we know. We also can see that it splits up into the ions in solution, which is what aqueous or aqueous means. And when that breaks apart, it releases energy. It releases 27.3 kilojoules per mole. And knowing that, and knowing that we're going to react 2 grams of it, we can make a prediction as far as how much energy that's going to be. So if we look at those pre-lab questions, we know that we have 2 grams of the ammonium nitrate, which is NH4NO3, and the NH4NO3 in our first problem, we have to calculate, how many moles that's going to be. So to do that conversion, this is pre-lab exercise number 1. To do that conversion, we need to know the formula mass of the ammonium nitrate, because our conversion from grams to moles requires a formula mass to do that. Okay, so using your periodic table, we can see that nitrogen has a mass of 14, hydrogen has a mass of 1. Oh, whoops, we got another nitrogen over here. So let's do 2 times 14 for those 2. And then lastly, we have oxygen, which is 16 grams per mole on the periodic table. All right, so adding that all up, we can see with the 2 nitrogens, 4 hydrogens, and 3 oxygens that we have a formula mass of 80 grams. All right, that goes in your denominator right here. So we're going to mathematically divide 2 by 80. And that gives us moles of 0.025, which is pretty typical for it to be small like that. In number 2, we're supposed to use that result and multiply it by the kilojoules per mole. So knowing that we have 0.025 moles of the NH4NO3 and 1 mole of NH4NO3 puts out negative 27.3 kilojoules of energy, we can figure out how much energy less than a mole would put out. Okay, so we're using the same kind of setup that allows us to cancel units out, right? We have grams and grams. Here, moles and moles are going to cancel out. So our answer comes out to kilojoules. So if we take the previous 0.025 and multiply that by negative 27.3, then we get a result of negative 0.6825. That's kilojoules. So in pre-lab exercise number 3, we're supposed to convert that kilojoule answer to joules, because our lab will be calculating joules, and we'll talk about that in a second. So we have 0.6825, ooh, that's an awful 5, 25 kilojoules. And then 1 kilojoule, again, I need my units to match so they cancel, is equal to 1,000 regular joules. Okay, so we're just going to multiply that by 1,000, which moves the decimal point over 3 spots. So we end up with negative 682.5 joules. All right, so I'm just going to box those answers real quick to help them stand out. In this last one, kilojoules cancels like that. So this is our act. This is the theoretical. Theoretical is going to be used later for when we calculate percent error. Because in the lab, you're going to experimentally determine the energy. And, but we know theoretically what that's going to be. So we can see how wrong percent error wise you are using this equation. So you take your experimental value minus the theoretical over the theoretical times 100 to get your units in percentage. And you really want that to be as low as possible. So we'll see how close we get to doing that. So let's just review the procedure here real quick. Oh wait, there's no procedure. There's no procedure because you're supposed to write it. You can use any amount of water that you need, but I'm going to use, I don't know, probably 50 milliliters. And because we're measuring energy, we're actually going to use the equation that we used before, which is the Q is equal to Cm delta T. Okay, C is a constant, 4.186. Mass is the mass of the water. I'm going to use 50 milliliters, which is equal to 50 grams, because the density of water is 1 to 1. So the only thing that we actually have to measure is the change in temperature of this reaction. Okay, so let's take a look how we're going to do that. Using the computer, we can measure the temperature. Right now it's reading at 19.9 degrees. I'm just going to check to make sure that I'm going to be collecting. I just really want to go for probably 3 minutes is enough. And I want to get 120 samples per minute. All right, so we should be ready to go. I'm gonna, should I do that right now? No, I can't do that yet. We have to measure our material first. Okay, so this is the ammonium nitrate. It's kind of weird looking. Little beady type things. We're gonna measure, and I'm gonna have the weighing pan on here just to make it a little easier. Looking for a scoopula here. I got a spatula, that's gonna take forever. We'll cheat a little bit. So it's reading at 0 grams right now. Watch me make a mess here. We're at 1 gram, 1.79. Can I even scoop these? Oh man. 1.3. Yeah, 1 chunk at a time. Good. Not even 1. All right. 1.97. Oh my gosh. I need like 1 more. Two. Counting it. Got 2 grams. All right, I'm going to be cheating. I'm going to use this device. It's a calorimeter. Calorimeters are specifically designed to measure energy. So I'm trying to reduce my error as much as I can. So that's 25 milliliters, and we're doing 50, so we'll add another 25. All right. Calorimeter comes with a nice little lid, but I'm not sure. Yeah, we'll be able to reach. Okay. So, all right, let's go back to the Logger Pro here real quick to start our data collection. Where are you, buddy? There you are. All right, so here in Logger Pro, we're collecting data now. You can see it graphing in real time. I'm gonna take my solid ammonium nitrate. The chunks didn't want to go in. And we'll be measuring that as I'm stirring. Well, let's watch the graph. A little hard to see exactly what's going on. So we can go over here to auto scale. See the temperature dropping pretty significantly there. Should find a low point. And it's going down because the energy is negative, remember, so. We're getting a flat line there at the bottom. Just came up a tick, so we might be done. It might have been the low point. Yeah, that might be it. Give it another second. All right, that's good. We have our data. Okay, so data treatment. This program's pretty nice because we can see a lot of the details right away. In statistics, we can see for that run that we had a minimum temperature of 17.06, maximum was 19. That might have been this up here at the very start. The temperature looks kind of weird because it was room temperature, and then I put it into the container, and so we're actually going to use max and min for our change in temperature. Okay, so I'm just going to write those down on the board while I have that open. All right, so our temperature max was 19.00, and our temperature min was 17.06. Those are both in degrees Celsius. Okay, so knowing that, and our equation, which has a change of temperature built right into it, we can use that information to figure out, I erased the, we can use that information to figure out your Q, the amount of energy that the reaction put out. Okay, so let's set that up. So we know in our equation that Q is equal to Cm delta T. We also know that C is a 4.186. That is joules per gram degree Celsius. It's got weird units because it has to cancel out the grams and the degree Celsius. So your answer comes out to joules. We're going to multiply that by 50 grams and by our change in temperature, which is 1.0. It's almost 2. 19 minus 17.06, 1.94. that's your change in temperature. So 1.94 degrees Celsius. And we're going to multiply the 4.186 and the 50 together to get 404.0. And you're probably wondering, wait a minute, didn't we say it should come out negative? Yeah, this is actually a negative temperature change because it was higher and then lower. So when you do temperature, it's final minus initial. So it actually is a negative value. So it's actually negative 404.0 joules. Now, if I remember right, it was around 280, I think, before, wasn't it? Somewhere around there. So when you do your percent error calculation, this is actually pretty bad, right? Because our experimental value is 404.0. I wish I hadn't erased that. And our theoretical was around 280 something. So you need to put that in, oops, theoretical. You need to put the theoretical in there twice and multiply that by 100%. Now, keep in mind that the theoretical, I just put this in as a positive. You should put the theoretical in as a positive too. It just makes it a little easier to calculate it. Or you can put them both in as negatives. It doesn't matter too much. But then you're going to multiply that by 100% to get your percent error. So I'll let you do that part on your own. So, and on the lab, that's your calculations part. So you do want to show the calculations I just laid out there. Also, don't forget to include the data. It would be great to have that graph that I just was showing. I might be able to screenshot that and attach it to this assignment. But then you do have to write up your hypothesis and talk about, you know, the information of the lab and possible errors and how you might improve that. You know, I did it pretty quickly and in one trial. It could be pretty easy to do this over again as a second trial to make it a little more accurate. You know, knowing the data that we have and the error that we have, there might be some thing we could tweak in the experiment to make it work. But anyway, hopefully that helps you figure out how to write that lab, and you know, then you can turn it in on the classroom. All right, thanks.